Today we have Joseph Bradley, and he's going to tell us something about sample complexity of learning CRFs, and he's going to present this work at AI.
Thanks. So yes, this is joint work with my advisor, Carlos Gestra, and I'm going to be talking about CRF parameter learning, conditional random fields, but I'll start out just by describing Markov random fields, which are a subclass of CRFs. And for the most part in this talk, I'll be discussing things in terms of MRFs just because of notational simplicity. But I'll point out where everything will generalize to CRFs. So our goal is to model some distribution, P of x, over a set of random variables, x. So maybe you want to model how a grad student is doing, and you have different random variables modeling their status, such as do they have bags under their eyes, is there a deadline coming up, that kind of thing. And the kinds of questions you might want to ask of this model are, what's the probability that the grad student has a deadline, given that he has bags under his eyes and is losing hair? Now, the way MRFs are going to do this will be by representing this distribution over the random variables x as a product of a bunch of these factors, psi, where these factors can be fairly arbitrary functions, and they implicitly encode a sort of structure among these random variables, where here you can see that this factor psi1, 2 encodes an explicit direct dependence between the variables x1 and x2. So given this product of factors, you can compute probabilities about the different random variables in this distribution. And the structure we'll see is what is useful in the computation and making that more tractable. So a useful representation for Markov random fields is the log linear form, where each of these factors will take the form of an exponentiated dot product between a parameter vector theta, which is just some vector of real values, and then a feature vector phi, which can take various forms depending on what your data look like. For example, if your data are binary, then phi might be something very simple, such as this vector of 4 indicator functions of the 4 different possible values 2 binary variables can take. But if you have real valued variables, then the features might be some whatever functions which some expert might give you, or you might figure out on your own, such as the sum of the variables, the difference, product, etc. So we won't concentrate on how these features are defined, but it is important to have an idea that they encode this dependence between the different random variables and essentially the structure of your Markov random field model. And I'll note that if each of these factors does have this log linear form, then the entire model can be expressed as an exponentiated dot product of a giant parameter vector theta and a big feature vector phi. So that's the form we'll be working with for the rest of this talk. And our goal is, given the structure phi, if you recall, these features implicitly encode the independent structure among your random variables, and a set of data, we want to learn parameters theta. So a very traditional way of doing this learning is maximum likelihood estimation, or MLE. So if you recall, our distribution is proportional to this exponentiated value. And our setting is we're given a set of n independently and identically distributed samples, IAD samples, from a target distribution, P theta star, where that star in the theta indicates that that's the true distribution or some target distribution you want to learn from. And we want to minimize this objective, which is just the expectation over our data points of the negated log probability of that data point. And this will be called our loss. So in a sense, MLE is a gold standard in that it's essentially optimally statistically efficient. In other words, it's the best you can do in terms of learning with a particular amount of data. But since you often don't have infinite amount of data, you often use regularization terms such as this in order to prevent overfitting. So this isn't the regularization is not a big deal in the talk, but I do just want to mention that we analyze it where you essentially penalize having very large parameter values, theta, and it's penalized according to this regularization parameter, real valued number lambda. And so our analysis will cover both L1 and L2 regularization, but you don't have to worry about it too much. So given that we want to minimize this objective, we can note that it's just some function of a vector of parameters theta. And so you can think of using some basic gradient-based method in order to minimize this function with respect to theta. So in general, there are more complicated or varieties of gradient-based algorithms, of course. But the idea is you iteratively compute the gradient, take some step along it until you reach some minimum. The problem with this is this computing the gradient step. And the reason, as you can see, is that I've been hiding this proportionality constant in the distribution. And when you actually write it out, it's written as this 1 over z of theta, which is called a log partition function or normalization constant. But it's a function of your parameters theta. And so on each iteration, you have to recompute it. This is called inference, which is provably hard for general structured Markov random fields and CRFs. And to get an idea of why, in order to normalize this distribution to sum to 1, you need to have this z value be the sum over all possible values of your variables x of this exponentiated term. And so you can see, basically, as the number of variables x increases, then the sum can take exponentially long time to compute. So you can see that inference makes learning hard. And what we'd really like to do is learn without having to do this intractable inference. So before I go into the rest of the talk, I do want to mention conditional random fields, since I promised to. But just to point out why this problem with inference is even more an issue with learning with CRFs. So Markov random fields have this distribution over some set of variables. But say you have some other values in the world, and you want to use those values, those observations, in order to improve your predictions, in order to improve your model of this distribution over x variables. What CRFs do is essentially let you do this using these extra observations or evidence variables e to improve your model over x without having to model this big structure over your evidence variables. So they take a very similar form, where it's just a conditional distribution, x given e. And what we want to note from here is that since you don't have to really model this structure over your evidence variables, then inference is not exponential in the number of evidence variables you have. And so this is a big plus with using conditional random fields. The problem is that this normalization constant will depend on your evidence variables. And to see why this is an issue, remember that the objective we want to minimize while learning is an average over your data points of this log probability of that data point. But now for each different data point, it'll have a different value for your evidence variables e. And so you have to recompute this normalization constant z for every data point when you want to compute your objective or your gradient. So you can see that inference makes learning even harder, in a sense, for conditional random fields. And once again, what we'd really like to do is learn without this intractable inference. So first, in this talk, I'm going to discuss some background on parameter learning because some work has been done on learning without intractable inference. The problem being, though, that before this, there weren't packed learning results for general MRFs and CRFs. We'll show that you can indeed get these kinds of nice sample complexity bounds. And we'll do it using what's called pseudolikelihood, which will avoid that intractable inference. We'll then look at an empirical analysis of these bounds, basically to show how tight they are or how loose they are in different situations, and show how these bounds depend on various model properties. And finally, we'll show that some problems which pop up when we look at the empirical analysis of bounds with pseudolikelihood can be solved by a generalization of that called composite likelihood, which will lower the sample complexity and avoid some of the issues with extreme model cases, but will keep essentially the same computational complexity. So I'll mention there has been some related work. The most relevant ones are probably, first, this work by Ravakumar et al., who did packed bounds for regression of a single variable yi given some other variables x using Ising factors. And they were discussing this in terms more of structured learning. But our theory is largely derived from this work. Then Liang and Jordan did an asymptotic analysis of pseudolikelihood and composite likelihood. And it's important to note that what we'd ideally like is for finite sample bounds to have similar behavior, and indeed our bounds do. And then finally, there's been work on avoiding intractable inference by using different types of approximate inference, like sampling or variational inference. The problem is that a lot of these methods don't, in general, have packed bounds for MRFs and CRFs. So we'll first look at some parameter learning background. So what we'd like to do, if you recall, is avoid the intractable inference involved in computing this log probability. So we'd basically like to replace this term in our loss. And we'll do that at first with a pseudolikelihood, or MPLE loss, which you can see is this sum over variables, every variable xi, given of its log probability of that variable given all the other variables, where that minus I subscript indicates just all variables other than I. So the intuition behind this is that you want to approximate a distribution as a product of a bunch of local conditional distributions, where in this case you have this entire distribution, p of x, and you want to say it's approximately equal to, first, the probability of x2 given its neighbor times the probability of x1 given its neighbors, and so on. And this is a pretty hand-wavy intuition idea, but there's been previous work on this showing empirically and in some theoretical sense that it's a good idea to do this. And so let me first point out that this doesn't require that intractable inference, because in order to normalize this probability, you only have to sum over values of a single variable, xi. And previous work has shown that this estimator is consistent, meaning that in the infinite data limit, you will recover the true model parameters. The bad things are that, first, it's been shown to be asymptotically less statistically efficient than maximum likelihood, and that there weren't packed bounds for general MRFs and CRFs. So in the next part, I'll talk about first how we can get that kind of packed bound, and then towards the end of the talk, I'll discuss composite likelihood, which will help us improve on the statistical efficiency. So next, I'll show our main theoretical results for pseudolikelihood. Now, there are already bounds for maximum likelihood. And just for comparison, I'll show them first, and then the pseudolikelihood bounds. But I want to emphasize that this, of course, doesn't deal with the computational complexity of doing max likelihood estimation. So the theorems will take the form of given n IID samples from this target distribution, maximum likelihood using regularization of a certain amount, which depends on the samples, is going to achieve an average per parameter error of this epsilon, which is that's measuring the per parameter error in the sense that it's 1 over r, which is the length of the theta parameter vector, of the L1 distance between the learned parameter vector theta and the true one theta star. And we'll allow this to fail with some small probability delta. And to make this all hold true, we'll need at least a number of samples n, which will be some constant, times a few factors. Now, to see what these factors are, first look at the log term. You can see that the dependence on the number of parameters, the length of theta, is pretty small, log of r. And then we also have log of 1 over the probability of allowed failure, which is pretty standard for sample complexity bounds. We depend on the desired target error, epsilon, as 1 over epsilon squared. So as we want to become more accurate, we require more samples. And then we have this problem-dependent constant, which is lambda min, the minimum eigenvalue of the Hessian of the loss at theta star, the optimal parameters. And what this is essentially measuring is how hard this problem is in doing learning. And you'll see in our empirical analysis later how this varies across different models and how this affects learning and practice. But essentially, the smaller it is, the harder the problem will be to learn. So our results for maximum pseudo-likelihood take a very similar form to maximum likelihood. And this is exactly the same formula. And recall for max likelihood, we have this lambda min problem-specific term depending on the eigenvalues of the Hessian of the loss. Now that term is the only thing which changes for a pseudo-likelihood bound. But rather than being the minimum eigenvalue of the Hessian of the loss at theta star, it's a minimum over variables I of the minimum eigenvalue of the loss component for that variable I. So what this is essentially saying is this term inside the outer minimum is very similar to the max likelihood estimation term. But then you can see that essentially each of these components of the loss is essentially estimating some local part of the parameters. And the reason we have a minimum outside of that is that if you have some component in here estimating some local part of the parameters, then if a single one of those gives a horrible estimate, then of course your entire bound, your entire estimate is going to be pretty bad too. So just quickly to mention one nice possibility with pseudo-likelihood. There's this question of how exactly you optimize this loss. Now, pseudo-likelihood technically is the sum over all variables of these local terms. And recall that our intuition is that we want to approximate this distribution as a product of local conditionals. Now, you could imagine optimizing this in the traditional way, like we've just been talking about. Or you could imagine taking each of these individual factors in our approximated distribution, these local conditionals, and noting that each one gives you an estimate of the factors involved in this local conditional, where you can see that as we estimate the local conditional, we'll get some estimate of those local parameters, theta 1, 2. And then when it's estimated, you estimate the max pseudo-likelihood. When you do max pseudo-likelihood estimation, you estimate all of these parameters, theta 1, 2, and the others, jointly. But you could imagine doing them all separately, where the idea would be you would essentially take one variable, x1, and regress it on all of its neighbors. And this would give you estimates of several of the parameters, like theta 1, 2, in this model. And then you would repeat that, regressing each variable on its neighbors. And this would give you a bunch of possibly conflicting parameter estimates for your model. the benefit of this is, of course, that now you have, rather than a single joint optimization problem, you have one optimization problem for every variable, and you could think of parallelizing it. So you can get sample complexity bounds for doing this. And they're pretty similar to the joint optimization bounds. But you get these extra terms, which are the number of variables, x, in your model. And so the con is that you have a worse bound, but the pro is that this is data parallel, so you can do it very quickly on a cluster. OK, so we've already seen these types of bounds where it's showing the sample complexity with respect to parameter estimation error, epsilon, and the number of samples you need to do that. But what you also might be interested in are bounds on the log loss. So this is a pretty standard kind of result, but basically says that if you are close to convergence, then the log loss is going to converge quadratically in epsilon, which which you can see at the end. But if you're far away from the optimum, then you'll just converge linearly in epsilon. And so basically what you can do is combine these bounds on the log loss with the bounds up there on the parameter estimation error, and in order to get a bound on how many samples you need in order to get a certain log loss. And I'll note that this matches the asymptotic rates, which we mentioned before in the related work. So we have these. We've seen that using pseudolikelihood, you can pack-learn parameters and pack-learn with respect to log loss for CRFs and MRFs. But of course, the question is, how do these bounds actually perform in practice? How useful are they prediction? And so we'll examine that next. Now, all these example problems will be with respect to synthetic conditional random fields, where we encode these conditional random fields by binary factors between pairs of variables over binary variables. And we'll use different types of factors just to give a variety of models. So one type of factor we'll use in encoding this are, quote, random factors, where essentially the log of the value of each factor value for all values of the variables x1 and x2, which are the arguments of that factor, will be sampled from a uniform distribution between negative s and s, basically to give a range of different types of interactions between variables. And then perhaps more intuitive associative factors, which essentially say that variables like to share values with some strength s. So essentially the important thing to note from how we are defining these factors is that this value s measures the factor strength. In other words, as s becomes larger, then variables have stronger and stronger interactions with each other. And we'll see intuitively that that will make models more difficult to learn. We'll look at a number of types of models. First on the left, we'll look at chains, which are just strings of variables. And the useful thing at this is it's essentially looking at how the bounds vary with model diameter. We'll also look at stars, which are basically one variable with a bunch of other variables, each of which individually interact with that center variable. And that'll basically let us examine how node degree in our models affects the bounds. And finally, we'll look at grids, which will be nice because they'll be an example of where maximum likelihood, which is, in a sense, the optimal estimation method, will have trouble because of computational issues. So first, looking at the tightness of the bounds. This on chain, small chain with random factors. On the left, we'll look at this bound showing that the parameter estimation error will be upper bounded by some function of the number of training samples you have. And on the right, we'll look at this bound saying that the log loss can be upper bounded by your parameter estimation error. So first on the left, on the x-axis, we have the number of training samples. And on the top graph, you can see that the true, from doing learning, the parameter estimation error is decreasing steadily as we increase the training set size. And this is what you would expect. The interesting thing is comparing the two, because on the top we have the actual parameter error, which was learned. And on the bottom, we have what would be predicted by the bound. And you can see that the dependence with respect to training set size appears to be fairly reasonable, but the constants are way off. And so you can see it's a pretty loose bound. One interesting thing to note, though, is that we had discussed max likelihood being presumably better than max pseudo-likelihood in red, which should be better than disjoint optimization of max pseudo-likelihood in green. And you can see that, indeed, the bounds do show this behavior, where the error decreases going down. So we can see that this bound is quite loose. But then, looking at the bound on the log loss, given the parameter estimation error, that bound, again, follows a similar dependence to reality on top, but constitutes a much tighter bound because, as you can see, the constants are not very far off on the y-axis. So just to summarize these plots, you can see that our parameter estimation error bound is quite loose, but the log loss bound, given parameter estimation error, is reasonably tight. So the interesting thing to look at will be, is this very loose bound still useful? In other words, is it predictive somehow? In particular, the bound predicts that the error should be approximately of the same order as 1 over this lambda min value times the square root of the log of r, which is the number of parameters in your model. So what we want to do is examine this dependence on these problem-specific values and see if this bound is indeed useful for saying how many samples you'll need for a particular problem. And we find essentially that it seems to be reasonably useful. Here on the x-axis, we're plotting 1 over lambda min. And it's on a log scale just so stuff isn't shoved together. But we should expect the error to increase steadily as 1 over lambda min increases. And indeed, it does. So on the top, we have the actual error from learning. And on the bottom, we have the bound. And of course, you can see that the constants, again, are far off. But we do indeed get this steady increase. And there's a lot of stochasticity in these estimates, but a noise in these estimates. But you can see that there's some kind of dependence on 1 over lambda min. The other thing to note is that we'd expect the bound not to really depend on the model size r. And indeed, it doesn't seem to. So in blue, red, and green, I'm plotting results for different size models. And you can see that they're all fairly overlapping, even on the top, in the learned parameter error. So that these bounds and the reality doesn't really depend much on the number of parameters r. So yes, as we stated, we've seen that the bound is useful in terms of showing how learning depends on these problem-specific constants. And in particular, it's important. The important value is this lambda min, which models how hard this problem is to learn. So recall that we have this distinction between what lambda min means for max likelihood and max pseudo-likelihood. And the question of interest is, how do these problem-specific values vary in terms of how max likelihood compares to max pseudo-likelihood? And we'd expect the max likelihood one to always be better, in other words, larger than the max pseudo-likelihood one. But the question is how large and how does that difference change across different models? So first look at this ratio of MLE to max likelihood with respect to chains. So what this plot is showing is that on a chain, as we fix the size of the chain, and we increase the factor strength on the x-axis. And as we increase the factor strength, the ratio between lambda min for MLE and MPLE is increasing steadily. And so max likelihood, which is what we want to optimize, max pseudo-likelihood, which is what we want to optimize, it does better the lower this graph is. So essentially, as the factor strength increases, doing the pseudo-likelihood approximation is going to hurt you more and more. Now on the bottom, this is showing for fixed factor strength what happens when we increase the model size. And you can see that the ratio jumps around, but it all stays at pretty small values. And using pseudo-likelihood doesn't seem to hurt you that much as you get a longer and longer chain. And if you think about it, this is pretty reasonable because pseudo-likelihood, if you recall, is basically, you can think of it as a very local approximation where you're just regressing single variable on its neighbors. So as you increase the length of this chain, each of those variables is pretty myopic. It's not really seen. The pseudo-likelihood estimate shouldn't be that affected by adding on extra variables way far away from the rest, from where you're making that local approximation. Now I'll show results for associative factors, and they'll be quite similar, although less jumpy. So again, on top, we can see as we fix the length of the chain, increase the factor strength, then pseudo-likelihood does worse and worse. And as we fix the factor strength, increasing the model size isn't going to hurt pseudo-likelihood that much. Now this was for chains and was really looking at dependence on model diameter. But if we turn and look at stars, which instead are looking at how node degree affects these bounds, then we get somewhat different results. Again, lower is better for pseudo-likelihood. And on the left, we have random factors, where here we can see that, as before, increasing the factor strength hurts pseudo-likelihood. And then we have a plot showing that as we increase model size, now pseudo-likelihood does get worse and worse. Before with chains, model size didn't matter that much, but now we're increasing the node degree, so we have really strong interactions with a single variable, and that's going to hurt the pseudo-likelihood approximation. And you get similar results with associative factors, so that right, as you increase both factor strength and model size, pseudo-likelihood gets worse and worse. So we've seen that there are some issues with pseudo-likelihood. Even though it's very computationally friendly, for certain models, it can be a bad approximation. So what we turn to next is called structured composite likelihood. And the idea there is that we'll lower the sample complexity, improving this lambda min ratio, but keep the computational cost essentially the same. So here's a motivating example. Max likelihood says that we want to have this model, and we want to estimate all of the parameters, like the entire model, at once. Max pseudo likelihood says essentially that we take every single variable individually, and we want to estimate its distribution given its neighbors separately. But you can, of course, imagine interpolating between these two extremes. And that's what composite likelihood is going to do. So we want to estimate a larger component, here shown in red, and indexed by some set of variables, YAI, where AI denotes a subset of variables instead of a single one. And we want to estimate this larger component, but choose the component in a way such that inference is still tractable. And I won't get into that, but you can essentially think of choosing components which are chains or trees or something very friendly like that, rather than big lumps and cliques and stuff. So composite likelihood has been proposed before. And the idea is basically you choose a bunch of these components and end up regressing them on their neighbors. And you can see how this interpolates between max likelihood, in which case you choose a single composite likelihood component which composes the entire graph, and pseudo-likelihood, in which case each of these YAIs would be a single variable. So I'll give you a little intuition about how you could choose these components. Basically, larger is better because intuitively that makes sense since max likelihood is the optimum, and that uses a component which is the entire model. But you want to keep inference tractable, so you have this trade-off between choosing a large component and one which is structured or sized such that inference is trackable. And finally, you want to choose it using the model structure. So what I mean by using the model structure is, suppose you have this grid example, and you have very weak horizontal factors, but you have very strong vertical factors. And suppose you had some expert knowledge letting you know this beforehand. Then a good choice for composite likelihood components might be combs like this, oriented vertically. With the idea being that essentially they'll capture, each of these components captures a lot of these strong vertical interactions. But there aren't many components, there are only two, quite large ones. And we'll note also that they don't overlap. So to show that this is useful, going to look at, again, this lambda min ratio, where, again, lower is better for the pseudo-likelihood or composite likelihood approximations. And on the left here, looking at increasing factor strength, and this is on grids for fixed size. Sorry, that y should not be 8. That should be grid width of 4 by 4. And you can see that it jumps around a lot, but basically as you increase factor strength, of course, both the pseudo-likelihood and composite likelihood approximations get worse, but you can see that the combs do significantly better than pseudo-likelihood. And you can see this more clearly with some of these other plots, showing that as you increase the grid width, then combs, again, do help ameliorate this issue with pseudo-likelihoods estimation getting worse. Do you have a question?
What error bar are you using?
The error bar.
Yeah.
So that's just, all of these are estimated from 10 randomly generated models, and then 10, for each model, 10 randomly generated data sets. And the error bar is just one standard deviation in either direction for with respect to the average over the 10 randomly generated models. So on the top, there's a lot of noise. On the bottom, it's reasonable separation, at least towards the right.
And why is it not symmetric?
I'm sorry?
Why is it not a symmetric error bar?
Let's see. So
it's a log scale. So
yeah, I think that is the issue. That's the log scale. Thanks. Right. So again, both of these estimators kind of get worse as some of these model parameters increase, but combs help ameliorate some of the issues with pseudo-likelihood. And you can see this clearly with associative factors too. So this is, keep in mind, with respect to the bound, where the lambda min ratio is what we're using to predict how many samples we'll need. What might be more interesting is an example of actually learning, where you can see that as we increase, I forgot the error bars, I guess, the grid size, then this is showing the actual log loss ratio. So the red line is the maximum pseudo-likelihood estimate compared to maximum likelihood, where lower is better. And the green line is the estimate using structured composite likelihood compared to maximum likelihood. And you can see that both of these approximations are getting worse as the grid size increases, but by using these structured components, you do significantly better in terms of log loss. So the structured components essentially do lower the sample complexity. And the interesting thing or the useful thing, is that they have essentially the same computational complexity as the pseudo-likelihood approximation. And both of those are, of course, much less costly than max likelihood. So you get lower sample complexity without really increasing the computation much. So I'll finally mention one last benefit of using these structured composite likelihood estimators. And notice I've been talking about using these combs chosen on grids, and this implicitly assumes that you have some expert knowledge telling you how to choose the structure of these composite likelihood components. But what you can actually show theoretically and in practice is that you can get some kind of averaging effect by using multiple overlapping components. Now the idea, which I'll just touch through quickly, is that we have this dependence on 1 over lambda min squared, and these are just the formulas for max likelihood and pseudo likelihood, which you've seen before. And for composite likelihood, you can get a very similar sample complexity bound, but it replaces this single lambda min squared value with what I'm writing as rho min over m max. So rho min is a minimum over a sum of components which estimate a particular parameter of the minimum eigenvalue of the Hessian of that component. And m max is this maximum over a number of components which estimate that parameter. But the important thing is not to clearly understand the thing in blue, but intuitively know that rho min over m max is essentially saying that rather than having a single estimate, a single estimator for each parameter, you may have a bunch of, say, overlapping combs, and that will give you a bunch of different estimates in a sense, or a bunch of different influences on your estimate for each particular parameter. And so if you have multiple types of components, like these combs, overlapping, then you, in a sense, get the effect of averaging how well each of those different components estimates that parameter. So to see what I mean, if you have, say, this very simple grid and use a maximum composite likelihood estimator, which just has these two components, then you can see that this factor is estimated by both components, since it touches both. But this factor is only estimated by 1. And in this case, in max, the number of components estimating a particular parameter, the maximum of that is 2. Similarly here, you could choose components going in a different direction. But you could also think of combining these so that you kind of average the effect of having these two different types of estimators. So you can see that in practice. What we're going to expect is that for max pseudo likelihood, a single bad estimator can give a really bad bound or a really bad result in learning. But for composite likelihood, if you take advantage of this averaging effect and you don't know how to choose the best estimator, then you can average the effect of several, and the effect of a bad one can be somewhat tolerated. So you can see this in practice where looking at grids, and this is the grid width plotting the lambda min, where larger is better. So maximum likelihood should be at the top, doing the best. And then max pseudo likelihood does significantly worse, definitely deteriorating in performance as the grid width decreases. If you use vertical combs on this kind of grid, then you end up doing somewhere in between the maximum likelihood and max pseudo likelihood approximation. And you can note that this is what we'd expect to be the good comb, because it's modeling these very strong vertical associative factors. Now, if you don't model those as well by choosing combs with which are oriented horizontally so that they capture fewer of these strong vertical factors, then you end up doing significantly worse. But if you average the effects of these, then you end up doing somewhere in the middle. So to sum up this empirical performance of these estimators, we've seen that increasing the model diameter has very little effect, and that pseudo-likelihood and composite likelihood are going to get worse as you increase the factor strength, the node degree, and the grid width. However, structured composite likelihood can partly solve these problems, where in particular, if you choose that composite likelihood, the component structure according to factor strength or node degree or some grid structure, then that can improve the sample complexity and without really increasing the computational cost from pseudo-likelihood. So to sum up, I've looked at pack learning via pseudo-likelihood and composite likelihood for general MRFs and CRFs. And through an empirical analysis with synthetic models, shown that the bounds are predictive in terms of empirical behavior and dependence on problem-specific parameters. But there are issues such as strong factors and high-degree nodes hurting pseudo-likelihood. And we've seen how structured composite likelihood can somewhat overcome this. Now, some interesting possible directions in the future are showing how to choose this composite likelihood structure on natural graphs. So you can imagine if you're given a natural problem and don't have expert knowledge telling you how exactly to choose this structure of the components you're using to estimate the parameters, then you might be able to develop some method which perhaps iteratively takes advantage of, say, your estimates of which factors are strong, or you could look at the graph structure and see which are high-degree nodes, or if there are grid structures you can take advantage of, things like that. You can also look at parallel learning. It'd be interesting to see if you could improve the statistical efficiency of disjoint optimization via limited communication. So not doing the full, very expensive, potentially expensive, joint optimization of pseudo-likelihood or composite likelihood, but instead estimating each of these components separately, but with some very limited communication in order to improve the sample complexity. And then it would also be interesting to look both empirically and theoretically more at how these different estimators compare with doing, trying to optimize the log likelihood where you estimate things using approximate inference. Now, there have been some theoretical work showing connections between these, but it'd be interesting to examine that further. So with that, I'll thank you. And